recording, so it's a second recitation or the second remote recitation. What I'm going to do, just a brief recap of the phylogenetic discussions that Diane had with you during the last week. And by the end, if you have any question, I can answer them. If you want me to explain the concept, I'll be more than happy to do so. But first and foremost, just let's go over the basics of creating a cladogram. So I'm using the term cladogram instead of phylogenetic tree. As I'm sure you know, there are distinctions. So let me write. So a phylogenetic tree versus a cladogram. So does anyone know what's the difference? By the way, you can also talk if you want to instead of writing at any point, but you can just write. So the difference between phylogenetic tree and a cladogram. What is it? What differentiates these two? In your textbook it has usually been used interchangeably, but yes, clades versus phyla. So clade, of course, it just means a group. That's Greek, I'm afraid, and phyla or phylum just means a branch. Again, from our Greek heritage. Now let's just draw some phylogenetic tree. I try to draw. It's going to be a little bit questionable because I'm drawing with a mouse, and that's not accurate, but I try my best. All right, so this is a phylogenetic tree, or a cladogram, actually. So a cladogram simply shows the relationship between different taxa. So again, the term is usually used taxon, which plural becomes taxa. So this taxa just refers to a group, a branch. So it can also or phylum. Phyla. So phylum or so phylum again plural, phyla, a taxon, plural taxa. So that those just refers to any node in this tree is a taxon. It can be a group, it can be a genus, can be species, what have you. You can have a tree of life where you just simply show the domains of life, eukaryotes, prokaryotes, etc. So these we can arrange these taxa or these phyla according to their relationship. And if we simply want to draw a tree where the relationships are shown, that is a cladogram. So it's a gram. So a gram just means a graph. A clad or clade just means a group. So it's a tree that represents the relationship between the groups. A phylogenetic tree, on the other hand, has additional information about the amount of change that has happened since the emergence of these species. So if we knew that like here there's like 20 changes here versus 2 changes, then that would be a phylogenetic tree because you have an additional level of information, an additional layer, which simply tells you if taxon B has changed more than taxon A. In those kinds of trees, actually, I don't think there are any of those in your textbook, not that I know of. In those types of trees, you usually end up with trees that look like this, where there are different taxa, but the branches have different length. So something like this, where the branches are proportionally drawn to reflect the amount of change during evolution. So that's a different story. You can also have trees where the changes are actually years. So it's like 20 million years. So the branches are drawn so they would reflect the number of years. So that's a chronogram. Chrono means time, and gram just graph or tree. So that's just the very basics of how to draw a tree and what type of information or what level of details you would expect to divine from any any different type of tree. But the question remains: how are you going to construct a tree? How is that possible for you to do so? Let's delete these. Just have more space. So I wanted to draw a tree. So this simple tree would treat with three taxa, A, B, and C. How could you construct it? That is actually done by studying characters. So the characters, and it is known that there are many characters associated with a given species or a given group of organisms or a given taxon. So the question is, what characters are informative? So does anyone know what does it mean for a character to be informative in this context? What would be an informative character? Morphological. So Jennifer pointed out. So there are different types of characters, right? Morphological, behavioral, or ecological. But that's just types of characters that you can study. They can be genetic as well. But the question is, amongst the characters that are genetics or morphological or behavioral, which ones are good for classification? So let's just give you an example, and then we can see which ones are human, gorilla, and chimpanzee. So the question is, what types of characters we should use to classify these three different species? Actually, so chimpanzee would be a group, not a species, because there are two. And let's say we have these characters. So you have speech. So the ability to speak is a character. Big brain. And what else? Bipedalism. And can we have another one? Group. Actually, these are so what would be a better character? Or actually, it's just a science. Science. So it's a hypothetical scenario in which we have these three different characters, right? So we have the Speech as a character. So we know that in human you have speech. In gorilla and chimpanzee you don't. They don't talk really. Not in a way that can be classified as speech. They do communicate, of course. Size of the brain and bipedalism is the ability to walk upright. So, in your view, which of these characters is least informative uh, in our attempt to classify humans, chimps, and gorillas? Anyone? So, what is the least informative character out of these three? Speech, size of the brain, or bipedalism? Mm-hmm. Anyone? So, since you are not providing an answer, I think a character that is limited to one taxon is very hard to be used for classification because you classify based on shared characters, right? In the case of speech, at least in the strict sense of the term, speech is only associated with humans. While the size of the brain changes from gorilla to chimp to human, and bipedalism changes as well because in chimpanzee, one species, you have some semblance of bipedalism. But the speech is purely a human faculty, and thus, since it's not shared amongst these groups, it can't be used to classify them because it doesn't give you any information about anything, since uh, uh, since you can't imagine or you can't postulate that the common ancestor of humans and chimps had the ability to talk because chimps don't. So you can't divine anything about the common ancestor, and hence you can't group them. So the classification is going to be based on characters that are shared, and amongst characters that are shared, there are two types of characters. So again, let's try to classify these groups. Right. So I'm just going to use H for human. So there are two species of chimps. So I'm just going to call one C1 and that one C2. And for the second argument, just assume that there is a gorilla. So G for gorilla. Now, in order for us to construct a polygenetic tree, I just told you that a character that is simply limited to one taxa, like speech, is not informative. So let's say this yellow line is speech. So that character doesn't tell you anything about the common ancestor of humans and these two species of chimps because chimps, they don't have this ability, so you can't say if that was shared. Also, gorillas, they don't talk, so that the character of related to speech doesn't tell you anything about the common ancestor here. So actually, let's name these common ancestors. So we can have a here. This is one. Two, and there's a common ancestor here, 3. Okay, so 1 is the ultimate ancestor, so that's the root of our tree here. All these species descended from that common ancestor, number 1. Number 2 is the common ancestor of humans and chimps, and in chimps you have 2 sister taxa. So again, so you hear people talk about sister taxa. So any 2 taxa that are related through a common ancestor are sister. Sister. Oh, there should be T here. Sister. Sister taxa. Actually, let's write it. That would be easy. All right, so any questions so far? So we have a bunch of species. They're related to each other through common ancestors. And we also discussed an uninformative character. It's a character that is limited to one taxa, one lineage, because it doesn't tell you anything about the common ancestor or the state of the character in the common ancestor. Also, it gives this. Okay. Now, so let's look at the character states. So let's say, so character states are binary in classification, or at least the classification in the way that we know it. So there's binary states. So meaning that you have it, you have the character, or don't. Right. So when we talk about a character, when let's say it's having a bright plumage, in the simplistic scenario, you either have it or you don't have it. We are not really, because it's an introduction to constructing a phylogenetic tree, we are not really going to have a more no, we're not going to have a gradient of characteristics. It's just going to be you have a character or you don't. And in the case of characters, you don't. You share characters. So here, let's say in chimpanzee, so in species 1 in chimpanzee, they have the ability So chimpanzees actually are cannibals. If you have seen any nature documentary with chimps in them, they eat each other. They also eat other monkeys. Um, they're very aggressive. And let's say that characteristics of the cannibalism, which we know for sure, gorillas, they don't cannibalize humans. It's not at the moment a widespread characteristic. Um, so we just talk about this character as shared between these two species of chimpanzee. So then this character, denoted by color red, is shared between C1 and C2. So it's a shared character. And we can say that the common ancestor between humans and chimps didn't have this character. So the number 2 didn't have that character. So it's a shared derived trait. So trait, character, it's interchangeable. Okay, so a shared derived trait between these two characters, between these two species, also known as synapomorphic. Syn means what is basic? Common. Apo means a way. Actually, I tried to find a word with apo prefix. All of them are technical words, so it wouldn't be helpful. Morphe just means character. So these are shared characters. So if you want to memorize what this means, you just need to remember that that this bit syn is shared and morph is just trait. And so that's a synapomorph. Now let's look at another trait that is shared. So the ability, okay, we are running out of colors. So let's use a blue. Okay. So second character in primates, all the primates they have have the ability to use. So they have opposable thumbs. So in great apes we have opposable thumbs, meaning that their thumb, as you can see here, moves somehow freely. So you can grab stick and use it as a tool. You can grab on branches better, stuff like that. And here I use blue to denote that. By the way, sorry, actually, I just remembered that if you're colorblind, some of these colors might look the same. I try to refer to them clearly, so even if you don't see the color difference, you can follow what I'm trying to say. But I do apologize if that's the case. So here, this line next to S, so in human, chimp, C1, chimp, the second species of chimp, C2, and G, gorilla, all of them have this trait of having the opposable thumb. Now, so this trait is shared. So it's a, so let's just with an arrow to the trait, it's a shared trait. But it also, we can assume that this trait, since all of them have it, number 1, so this ancestor also had it. So it should be here as well. Because, well, I discussed later why that should be the case. So it's shared, but it's ancestral, since it comes from the ancestor. And it's a trait, as usual. So it's a shared ancestral trait. Or same plesiomorphy. Again, just for simplicity, same like sin in the previous one, just means shared. Plasio means ancestral, and morph is a character or a trait, is morph. So the shared ancestral trait amongst these species. Simple as that. Now, in the previous argument, when I was talking about the fact that presumably, since all these four species have the character of opposable thumb, uh, it's reasonable to assume that the ancestor, the number one, also had it. Why should it be? Why not assume that the ancestor didn't have the trait in question? The trait appeared, so I'm just going to use an alternative form of evolution. Use different color. So what if? So ancestor didn't have it. This number two acquired that trait, and also in the gorilla it was independently evolved. Why isn't that a plausible explanation of what has happened here? Why not have two changes instead of one? Anyone with any suggestion on why not? And again, you can type. You can also talk if you. I think if you raise your hand, which is the button on the top left of your screen, you can raise your hand and you can talk. So no one. Okay, so the idea that having a single change is better than having two changes relates to a principle that is used, or one of the ways by which you can construct a phylogenetic tree is the principle of parsimony. Parsimony or lex parsimoniae. Lex parsimoniae, just Latin. Lex means law, so it's the law of parsimony, also known as Occam's razor. It comes from William of Occam, although you can trace it back to Aristotle or Maimonides. So it's a very old idea. So the idea being that whenever you have alternative explanations, the explanation with the fewest assumptions is preferable. In different contexts, it means different things. In phylogeny, though, and in cladistics or taxonomy, the science of constructing trees representing the relationship between different organisms, the principle of parsimony simply means that the most plausible scenario is the one in which you have fewest changes. So a tree, okay, so a tree like this, let's say, so let's say we have two alternative trees. Actually looks kind of no. All right, sorry. Okay, so we have, let's say I have two trees. The second one is this. So we try to relate three different species. What happened? All right, A, B, C, here. B and C. And in each tree, there are a number of changes that resulted in you constructing this tree. So let's say B and C, they share a character, while A has a different state of that character. In this case, this one B and C. So in both of them, B and C have this shared character. But in these two branches, in one of them, we grouped A and B together as sister taxa. In the other one, let's call this one number 1, and this one number 2. So in the first tree, we have B and C together. In the second tree, we have A and B together. So in your view, based on the principle of parsimony, which one is the preferable tree, number 1 or number 2? One. So why is that? Why was it immediately obvious to Jennifer, Chris, and Sylvia that number 1 is the clear winner? There's only one change, as Jennifer pointed out, and I think Chris is also going to point out the same thing. There's only one change, right? As you point, as probably all of you have noticed. So in the first one, synapomorphy, symplasiomorphy. Oh, okay. So yeah, shared drive traits preferable. But aside from the distinction between synapomorphy and symplasiomorphy, which Chris pointed out as a very astute observation, the main point I want to make was that in tree number 1, you just need to assume that there was a change that happened in the ancestor of B and C. Versus in 2, you need to assume that in lineage B, a change occurred, and in C, an independent one occurred. So you have 2 changes versus 1, and that is preferable. Mind you, that doesn't tell you if that's actually what happened. I mean, it could be that B and C independently acquired the trait in question, and surely that can happen in the case of homoplaces. So if number 2 actually is the true tree, it's a case of homoplasy, right? When they have characters they have the same characters but independently acquired, so it's a parallel evolution for you. So that can happen, and usually the way to avoid these, or the way to get to the tree that's a true one. So you have a hypothetical tree and you have a true tree, which is the actual tree that represents the way that evolution unfolded. Though usually that's impossible to construct since you can't really test all the possible trees. Now, one might say, why not create all the possible trees and match it with the characters that we have to get the true tree? Why have these principles that are heuristics, that they're ways of doing things that are not necessarily that doesn't give you the exact answer, but they give us a very, very probable answer? Why not just go exhaustively, create all the possible trees, and pick the one that is the true one? Why not? Can anyone answer? Just too many trees. So the combination is a problem of combinatorics. So in this case, you have A, B, and C. So it's so you have 3 things. You want to pick 2. So groups of 2, because then that's how you group it. I mean, that's also the simplistic one. So in this case, we have what? So there's 3 possibilities in this case. So 3 ways to group 2 together. If you increase this number 3 to 10, the number is going to explode. And usually in a taxonomy, in a phylogenetic tree, you'll have more than 10 taxa. So then that would become, so let's say in the case of 10 to the power of 2, sorry, 10, this mouse. So 2 out of 10, that would be 1945. That's only the groups of 2. Now you have to embed those groups of 2 into groups of 3 taxa, and etc. So it's a nested tree. So the combinatorics is going to be a little bit too much for the computers to do. Actually, people who deal with a lot of taxa, they spend months analyzing the trees, and their computer is just crunching numbers to get to some tree that is not the true tree, but just some semblance of it. It's the most plausible one. That would give you that, and even that would take months for anyone to do. So that's just a pure problem of computational power, just the number crunching being too much for us to do in our lifetimes. Now, so there are other models discussed. You're not going to use them as a maximum likelihood method. And there was actually another one. What was it? The Bayesian methods, which again, you're not going to use the Bayesian method. The Bayesian method is actually very complicated to use. And again, one thing you have to take into account is that the principle of parsimony, or the simplistic scenario that I just described, assumed that there was no gene flow, horizontal gene flow between these taxa. So if you had flow of information from these taxa and also these ones, then all the estimates of relationships are going to be affected by it. So take into account all the possible changes and all the ways by which the changes are going to be shared, ways that have nothing to do with just this branching and speciation, but they have to do with migration and gene flow, etc., etc. That just complicates the matter. There's one interesting actually topic touched upon in your textbook. It's about the bootstrapping. So bootstrap. Is it? Are there double P's in it? Strap. Are there double? Yeah, they are double P's. So that was not a mistake. So bootstrapping, and that's very interesting because that gives you, usually you don't have a million of data points to use in order to get some real tree. And there's a problem is that how confident are you that your tree is the best tree or the most probable tree? So the level of confidence, and bootstrapping is a way. Bootstrapping is not actually some method that is limited to taxonomy. It is a way that physicists and mathematicians have been using. Most of physicists trying to do simulations or analysis where you don't have your sampling and there's a probability associated with it. So you're not actually measuring the real things, but you're simulating the stuff and you have a sample of these simulations. And bootstrapping is the idea that you sample with replacement from your data and reconstruct the tree. So let's, so it is sampling with replacement. So what does it mean? What it means is that, let's say we have these, so in the tree 2, so actually let's draw a new tree because that would be a little bit. So let's say we have 3 species, A, B, and C. And we have 4 characters. So it's a character 1, it's character 2, and character 3. In the case of each species, there are values associated. So let's say A doesn't have a character 1, but B has, C has, while this one is like this, and this one is right. So you have several characters, and you have 3 different species with the characters associated with them. So the idea of bootstrapping is that in order for you to get a confidence level of how probable is your tree, you just use these. So you have 3 characters, so you try to sample with replacement characters out of all the characters that you have. So let's say when you sample, which is just random pick, so you want to pick 3 characters out of these 3 characters, and you end up with, so sampling with replacement means that you can get so in one of these sampling, by just chance, you can get character 1, character 2, and character 2. In another one, you can get character 1, character 1, character 1, etc. Right? And each time when you sample these characters, you construct a tree. And so you get a set of trees constructed by these resampling. And so in these trees, you can have, you see that, oh, these the sister taxa A next to B is present in 95% of those trees constructed through the sampling with replacement. So then you have 95% chance of getting it. So you can calculate the confidence interval based on the probability of you getting the same tree over and over again using different sets of characters, where you can also have duplicates of the characters in question. So that's about it. I tried not to answer any question from the homework because I shouldn't, but the homework is actually about these ideas, so you should have an easier time answering the questions. If you have any questions, just feel free to answer. Otherwise, sorry, feel free to ask, not answer. Otherwise, I am done with my little recap of what happened in the last week in evolution sessions. So any question or comment or concern? I don't know with that. Oh, so yes, so at the bottom, so these, so I'm sampling 3 characters out of the 3 characters that I have, and since it's sampling with replacement, that Jennifer asked about the bootstrapping. So since it's sampling with replacement, I by chance I can pick the character number 2 twice, or just pick the first character, etc. So you get a number of possible combinations of these characters, and then you construct a tree based on that. Kristen says, did you say that bootstrapping is a problem of getting character in a certain order? Yes, I would say that. So it's the probability of you getting the same arrangement of taxa in a tree given the characters that you have. So So let's say, so in the example phylogenetic tree number 1, if the B and C next to each other, so B and C as sister taxa happened in 90% of these trees based on these reshuffling of the characters that we did during bootstrap, then there's a 90% probability that you would get them regardless of what characters you pick. So it means that it's not really just based on a character. It means that if you just combine the characters and mix and match, you still get the same 2 taxa next to each other. Hopefully I answered Kristen's question. As a Christine, as a, I should apologize for any butchering of your names. Not really my strongest suit, but I try to pronounce them correctly. All right. Apparently, I did answer Kristen's question. So, any more questions? We will have a normal session on Monday, right? And as usual, these remote sessions are going to be online on the said on the YouTube channel, the address of which, or the name of which, is actually on Blackboard. I've already uploaded. Actually, I did it last week. I uploaded the recording of the last or inaugural remote session, which actually is kind of choppy. Hopefully, this one is better. It looks like it didn't have the same problems that we had. So if there are no questions, we can conclude. Oh, sorry. Jennifer asks, how is Boolean different from Bayesian or odds ratio testing, or do we need to know? Do we not need to know that? So Bayesian and odds ratio. So Bayesian is odds ratio is maximum likelihood method, which I don't know how. Like you really don't know enough, and the textbook doesn't tell you a lot about it for you to use it. Bayesian as well. Bayesian is characterized by a prior probability. So I can tell you that much that saying, let's just write it here. Saying Bayesian is there's a prior probability. So that's the whole point of Bayesian statistics. That's actually a different type of statistics. Where, as opposed to the normal statistics, so when people teach you statistics in undergrad or even in graduate school, the default is what you usually call the frequentist statistics, which is how you calculate mean and standard deviation, and how you do t-test and chi-square tests, and all these tests. And in none of these tests, at least not explicitly, you assume any outcome. So you don't really you pretend that you have no expectation whatsoever. So when you do t-tests, the way it's constructed is to pretend that we have no idea what the outcome can be, and hence we make no assumption, or at least no explicit assumption. There are implicit assumptions in that as well, about the normal distribution and etc. Yes, we don't not only so in frequencies you usually have a null hypothesis, but you don't really expect any specific. You don't explicitly expect any specific outcome. But in Bayesian, the idea is that we know about the outcome. Like we have in a lot of cases we have a level of certainty about certain outcomes, while we are uncertain about other outcomes, right? And so the entire method is based on the idea that you have a prior probability and you try to test if the prior is suitable. And the entire test is built around feeding the prior into our statistical model and taking that into account. Having said that, what it means in phylogenetic trees is that it gives certain weights. So let's say that we We want to construct a phylogenetic tree. And again, this is the most basic way to explain it. It's a very complicated area. I, by no means, am an expert. I just have a cursory knowledge. I've used Bayesian a little bit, um, but not a lot to be an expert. So let's say we have these this phylogenetic tree, right? Or these three taxa. And we have traits associated, associated with different, with these different phyla. So we have these two. And we know for a fact that the reason B and C have the same character is because of parallel evolution. So we know for a fact that they evolved to have these characters, the exact same characters, independently because of the different evolutionary forces operating in the same environments, the same way that some marsupials have characters that parallel mammals, even though they evolve in different areas and they're not related, and they don't have they're not intimately related. Or they do have a common ancestor that goes way back, but they don't have immediate recent common ancestors. So in this case, we know that C and B, they shouldn't be grouped together because C and B had evolved in parallel. So in the case of Bayesian, you just give more weight to trees. Again, it's a very simplistic way of explaining it. You give more weight to trees where C and B are not together, where this parallelism has taken into account. So you give it a